Hello and welcome to this video. I would like to show different methods for multiple access, space, frequency, time, and code division. What is the background of these methodologies? You have the air as your medium and you want to share the air, your medium, among different participants. And for the communication you can vary different dimensions, and these dimensions have to be divided for different users to realize multiple access. Using these approaches you need guard spaces to reduce the overlap, and that means of course for different technologies different approaches to realize these guard spaces. And as the main effect of this multiple access methods, you will be able to share the medium under different users. So many participants can use this one medium, the air. First approach we want to look at is the space division multiple access. Space means that you somehow think about the distance of the antennas, and by space division multiple access you realize the communication in different areas which are far enough from each other so that the communication is not disturbed by the other communication in the far distance. And the trick is to do it in such a distance that the transmission range of one communication pair does not disturb, does not interfere with the transmission of other communication partners. Here a simple example. Think about base station A and base station B. Both have a certain transmission range, and the transmission ranges do not overlap such that a certain area is covered and there's a certain gap between these areas. If you position these two base stations in such a way, then you realize space division multiple access. In between there's a guard space for the reduction of the interference between these two transmissions. If you realize that in a more complex scenario with space division multiple access, then it could be that you have different base stations, A, B again, and other base stations as well, like these here, C, D, E, and F, and around each base station there's a certain transmission range, and as you can see these transmission ranges do not overlap. So this is the ideal case for space division multiple access. These transmission areas, these areas which are covered by the different base stations, do not overlap and do not interfere with each other. Space division multiple access. Now when I say transmission range, then you actually have to think about two more ranges. Transmission range is only one range which you would think about when you talk about transmission from a base station or from a sender to other receivers. The transmission range is the range in which it is possible to communicate. So the sender sends a signal. Within this transmission range the signal is received by a receiver with a strength high enough, with enough energy, and the receiver can also transmit its reply back to the sender. Then you also have the detection range. Detection range is a bit larger, and that means that you can detect that there is a sender. You can also detect that the sender might send some information, might send some packets, because you somehow can realize with your receiver that there is something in the air which looks like a packet. But you are not able to decode it. There might be too many errors in this packet and you cannot actually receive it properly. And the third range is the interference range. The interference range means that if you have another sender receiver, let's say you make another communication here in this range, then you cannot detect the signal from the base station A in the center. You cannot detect that there is some communication going on. You cannot see that there are packets transmitted from the sender A in the center, but you are interfered, your communication is interfered by the transmitted packages from sender A in the center. So that means there is additional noise from this sender which distorts your communication between, let's say, C and D. And this makes it a little bit more complicated for you to communicate. Depending on the noise level, it's more or less difficult to realize the communication. But you cannot actually see that there is communication from sender A or from somebody else going on. You just realize that there is background noise. This is the interference range regarding to the sender A in the center of this picture. Now the second approach is our frequency division multiple access. So we now take care about our frequency, the frequency we use for the transmission of our signals. And here on the upper right side you see there are possibly different frequencies you would like to use, different frequencies you could use for your transmission. For example, in the left picture there's a higher frequency, frequency 1, and you would transmit your signal with this frequency. From a sender to receiver, you use this frequency 1. The second picture shows that there is a lower frequency, which you might use from sender 3 to receiver 4, and the second communication pair therewith uses a different frequency to communicate their information. And now you have actually divided these two communications by the frequency. And that's all you need to do for frequency division multiple access. You need to choose different frequencies for different communications going on. The frequencies should not overlap, they should not interfere each other, therefore the frequencies have to have a large enough distance from each other. Now, how does it look like in our example with base stations and with mobile users willing to communicate? You might have one base station, and this base station uses different frequencies for different communication links which need to be established. For example, user 1 in this case uses a higher frequency and user 2 uses a lower frequency. And if these two users only listen to these dedicated frequencies, F1 and F2, the communication does not interfere and the users are divided by the frequency. Now again, a little bit more complex example. You have the frequency on the x-axis and you have the signal strength on the y-axis. And if you talk about only one frequency, you would have this in this diagram like a peak here and another peak in another frequency, and this might be F1, this might be F2. But actually in reality you don't have peaks like this. You rather have frequency ranges in which you are able to communicate. Frequency range for F1, for F2, and maybe also for other communication partners, and they use other frequencies. And here in this case you can again see this guard space, and if you use frequency division multiple access you have the guard space regarding to the frequency. So this is here the guard space you need to divide the frequencies the communication partners from each other. Another possibility to realize multiple access is the multiple access division by code. By code means that for each communication partner you use a distinguished chipping sequence. The chipping sequence is a kind of code, and the code you use for coding the original information in order to put it on a channel. These codes need to have a certain distance from each other. This might be something like the Hamming distance, for example, where you can calculate the difference between two codes or between two information blocks. And in this example, we have in the first diagram the information which is to be transmitted, and let's say you have a 0 and a 1. In the first part of the transmission you want to transmit the 0. After that, in the second part, you want to transmit the 1. And if you now use this code division multiple access, you have to XOR this information, the 0 and the 1, with a certain chipping sequence. The chipping sequence is shown here. This is this 0, 1, 0, 1, 0, 1, 1, and so on. And this is a chipping sequence with a higher bit rate. This chipping sequence is then XORed with the original signal with the 0 and the 1, and the result is the transmitted signal. You see the result in the lower right corner in the diagram. And if you compare it to each XOR operation, you see that it results from XOR of the chipping sequence with the information which actually needs to be transmitted. The transmitted signal then is the bit sequence you would actually send over the channel. It has a much higher bit rate, as you can see here, and this means that you also need a higher frequency than just transmitting the user data 0 and 1 with a much lower bit rate. So code division multiple access requires this chipping sequence, which is XORed with the user data, resulting in the transmitted signal. If you then have different chipping sequences, then these of course lead for the same user data to different transmitted signals. And this also means that at the receiver you have to know the chipping sequence, with which the original user data were XORed, such that you can decode with the same approach, with almost the same approach, the transmitted signal to the original user data. So that the receiver can again see this 0 and 1 here in this case, which was sent by the sender. And you might imagine that if you use the transmitted signal, XOR that with a chipping sequence, then you get the original user data. If you use these chipping sequences, you could compare that with the use of different languages which are spoken in one room. Imagine you would have some people speaking German as a mother tongue, other people speaking Japanese as a mother tongue, and probably if you would stand close to each other, all the German and Japanese people, you would talk in your mother tongue, then you would be able to immediately decode your mother tongue, because it's much easier for you to understand German or Japanese if you are from Japan. So you have an internal chipping sequence, so to say, and you XOR that with the entire noise in the room, and then you're able to filter out your mother tongue such that you understand the communication. This is just to imagine how this works with the chipping sequence. Now let's have again a short look at an example in cellular-based communication. Again, we have a base station and we have different users communicating in this transmission range of the base station, and therefore each user would get one chipping sequence, one distinguished chipping sequence, such that the communication between the base station and this user 1 or user 2 is XORed with different codes, and that the base station is then able to decode both users at the same time. Now let's have a quick look into a frequency diagram if you consider this CDMA approach, this code division. Then you might have the signal strength here, and what you receive at the receiver is just a constant noise if you look into the channel. Now you take your chipping sequence into this noise, and you get your signal out of this noise such that you can receive the signal for your dedicated chipping sequence. All the other communication partners are still left in this noise. You don't get any information from these other communication partners. You just extract with the chipping sequence the signal from your communication partner, from your sender, out of this noise. Now the last multiple access method is the time division multiple access. And time, as you can see, we take care about the time. We dedicate time slots to each user. And for example, time slot 1 for user 1, time slot 2 for user 2, and therewith we share the medium by the assignment of different time slots. Again, we look into this example for cellular communication. We have the base station communicating with user 1 and user 2. The user 1 uses the first time slot, and the user 2 uses every other time slot here in this example. So broken down into this diagram of time and usage of the channel. First, user 1 would transmit its information or would receive its information. Then there's a guard time, and then there's user 2 communicating. After that, user 1 again, and they exchange their time slots for the communication.